I want to discuss unrestricted hard-to-fog. I hope you have sort of heard the difference between restricted and unrestricted. If not, you get sort of short repetition of that. And then it's in a way it's thought as a preparation for DFT, which comes later, where you will have, I mean, as soon as you try to calculate energies of radicals, actually you're going to do that in the afternoon also, but if you do that with DFT, these are going to be unrestricted DFT calculations, because that's the standard what you do. And there is a problem there which you should be aware of. And let's illustrate that problem for the hydrogen system, because there we can write things up. So we do unrestricted hard-to-fog called UHF for H2 hydrogen molecule, again in that minimal basis we had before. In the restricted, I mean, as soon as you talk about unrestricted hard-to-fog, you have to distinguish it from the restricted hard-to-fog, and then you put an R in front of it, RHF, restricted hard-to-fog. There we had, in the minimal basis set, we get two spin orbitals. Two occupied spin orbitals. We had the sigma G, which has a normalization constant, which is not important today. And then it was the basis function, the 1s basis function on hydrogen atom A, plus the corresponding basis function on hydrogen atom B. That's the spatial orbital, and if I want to make a spin orbital out of it, I multiply that with the spin function alpha. Then I have an alpha spin orbital, and I do the same for the beta. The spatial part is precisely the same, but now I have a different spin function. So the two spin orbitals in restricted hard-to-fog, the spin orbitals are made from the same spatial orbital, one with alpha then and one with beta. In unrestricted hard-to-fog, it's slightly different. In unrestricted hard-to-fog, I remove the restriction that the spatial part of this alpha and beta has to be the same. They can vary now. And since I still make them from the same basis function, the only thing I have to do is I'm allowed that this symmetry is broken. Here I have that in this simple case that the A and B basis function contribute equally, and then obviously I'm going to have the same also for the other. But if I want to allow now them to become different, then I can do that by just saying that I have put a coefficient C here, a constant C, in front of the B basis function, which I have in the alpha, and then obviously the normalization factor is also going to change. And the beta version is then, in order for them still to be orthogonal, is then this function. So these are the spin orbitals for unrestricted hard-to-fog. And now if you would do a hard-to-fog calculation, I mean, minimal basis set, hydrogen molecule, hard-to-fog calculation is finished in one iteration because there's nothing to determine any longer there. And here you would find an optimal value of that coefficient C for whatever internuclear distance you choose. So that is going to vary. So the unrestricted hard-to-fog wave function then, still being a Slater determinant, that is then proportional, forget about the normalization constant, that's proportional to the following expression, sigma G, alpha and beta, And because, I mean, this is, and that's electron 1, electron 2, but it's Slater determinant, it has to be antisymmetric, so I have to interchange them, so I get sigma G beta for electron 1 and sigma G alpha for electron 2. So if we expand the determinant, that comes out of it, like always. The diagonal would be that, and that's minus the off diagonal. Let's have a look. Let's insert our orbitals and see what that is. I forget about all those normalization constants. They are not really important. So if I insert now sigma G alpha and sigma G beta there, and I keep them in the order in every product of two functions. The first one is always electron 1, the second one is electron 2, like always. So what I end up with, I get this coefficient C, this one, and then I have chi A plus chi B. Then I get another term, chi A, chi B, plus chi B, chi A, parenthesis, and then multiplied with the spin function alpha beta minus beta alpha. And minus here.
Oh, there it is, sorry.
That is essentially that minus then. But there comes another term, plus 1 minus C squared it is, yes. Chi A, chi B, and then alpha beta, no, beta alpha, sorry, beta alpha, minus chi B, chi A, and here's the alpha beta. That was just inserting those two unrestricted spin orbitals in that determinant. So let's look at all the terms. We had some of them, these kind of terms before. What is that? What represents that? So I have electron 1 in a basis function placed at atom A. I have electron 2 in a basis function placed at atom B. So that's a situation where each atom has its own electron. And here just here, the other way around. Whereas here, I have both electrons either on A and none on B, or both electrons on B and none on A. So this is again, this is the ionic form, and this is the covalent representation, the one where they dissociate, if I would go to the dissociation limit, into two atoms. We come back to that later. But let's look now first we have this parameter C in there. So if C would be 1, this thing disappears. We have 1 standing here, which means we have equal weight of ionic and covalent. That is just the restricted Hartree-Fock. I mean, obviously, if C is 1, I'm back up there. So that's restricted Hartree-Fock. I have ionic plus covalent contributions. Let's look for the other extreme. Let's go C equals to 0. If C goes equals to 0, then I have no ionic contributions. And let's assume that let's sort of assume we're still in the dissociation limit again. No ionic. Great. in order to get this ionic removed, with restricted Hartree-Fock, we had to add the double excited determinant. We had to do a multi-configuration or multi-determinant wave function. We had to do CI. In our minimal basis set, we had to do a full CI calculation in order to get the ionic removed, meaning we included correlation. But if I do unrestricted Hartree-Fock, just unrestricted Hartree-Fock, still one determinant expression, one determinant, nothing more, but with unrestricted orbitals, and that coefficient gets small, then actually I get a wave function where the ionic also disappeared. Which means there's actually some correlation included in an unrestricted Hartree-Fock calculation. You have some amount of correlation included. So it actually has the potential to get you a better energy. Well, we'll see that. But an energy where there is some correlation included, like you would get if you do a CI calculation. And that means unrestricted Hartree-Fock is able to dissociate correctly. Because the ionic can disappear, the C just has to become smaller and smaller. And in the dissociation limit, it goes to 0, then this is gone. Well, you could say, you still have this one. With C equals to 0, you have this one fully. But look at that. That's again, one electron A, one electron B. Or one electron B, one electron A. So that's also covalent. So that also dissociates to atoms and not to ions. So the unrestricted Hartree-Fock dissociates qualitatively correct. It dissociates into the atoms. So it's like the CI correlation is included.
But
yes?
Subtracting something, I mean, what about this spin?
Yeah, that's what's coming now, yeah. That's what's coming now. And remember, I mean, unrestricted Hartree-Fock is a variational method, like restricted Hartree-Fock, so this C is going to be optimized. So if it can get lower energy by choosing a lower value of C, the method will do that. But what about the spin? Those two parts, they had the proper singlet spin function. What is this? Well, in order to see that, we have to go back to Tuesday and to all the single excited determinants we were talking about on Tuesday. And we had one. I wrote a triplet combination up of a singlet excited determinant, which looked something like this. Sigma G, sigma U, that's a single excited determinant. And I needed two of the single excited determinants, the one which had alpha and beta alpha. I had to make linear combinations of the two in order to get the, and I think it actually called it something like, I think it was 3' or whatever. I make the linear combination, so I get sigma U, sigma G, and then I got alpha beta plus beta alpha. That's the triplet spin function. So that's ms to 0, plus and a half, minus and a half, plus and a half, or minus and a half, plus and a half, so it's m, but it's s equal to 1 component. Now if I s lobby as before, insert now my orbitals in there, the same sort of unrestricted orbitals. Then I end up with that being chi A, chi B, minus chi B, chi A, times alpha beta plus beta alpha, which writing the product completely out gives me chi A, chi B, alpha beta, plus chi A, chi B, beta alpha, minus chi B, chi A, alpha beta, plus chi B, chi A, beta alpha.
B minus less 2.
Thank you. Those two. So what do we see? Those extra terms which come in the unrestricted how to fuck, those are actually terms which we have in a single excited determinant. So far so good. But with a triplet spin, half of it, that's half of the of a single excited determinant, but with a triplet spin. And that's in a function which is supposed to be a singlet.